Hi everybody. In this video I want to do an example in which I calculate the magnetic force that a magnetic field exerts on a moving charge. I want to do this two different ways. First, I'll rewrite the cross product in terms of a magnitude and get the direction by the right hand rule. So both of these things are contained in any cross product. And then secondly, I'll work out this calculation with full-blown vector notation, writing the velocity of the charge and the magnetic field vector in terms of the x hat, y hat, and z hat unit vectors, and then working it out using our vector math. So here we go with the first method. Rewriting this in terms of a magnitude and direction. So any cross product, the magnitude of any cross product will be the magnitude of the first vector. That'll be absolute value q times v magnitude in this case, multiplied by the magnitude of the second vector in the cross product, multiplied by the sine of the angle between those vectors. So that's just using the rule for getting the magnitude of any cross product. All right, so we'll calculate the magnitude and then we'll get the direction. All right, so for the magnitude of the magnetic force, I need the absolute value of the charge. Well, in this case, I've got a negative 10 to the minus 6 Coulomb charge. So I'll take the absolute value of that. We have the magnitude of the velocity. Well, I've got a velocity in this direction. I've indicated here that its magnitude is 10 to the 6th meters per second. 10 to the 6th per second. I need to multiply that by the magnitude of the magnetic field. I didn't write the magnitude of the magnetic field down. Let's assume that the magnitude of that magnetic field is 2 Tesla. So the direction of the magnetic field is this way. Its magnitude, given without an arrow over the B, 2 Tesla. And I need this factor, the sine of the angle between the vector constructed, well, the sine of the angle between V and B, that's 30 degrees. So I need sine of 30 degrees. And I can work all that out. The sine of 30 degrees is 1/2. So I have absolute value of 10 to the minus 6, that'll kill the minus sign. 10 to the minus 6 and 10 to the 6, that's 1, times 2, times 1/2. The units, I've got Tesla, meters per second, Coulomb, that's a Newton. So all the numbers come out to 1, all the units come out to a Newton, and I've got a force of magnitude 1 Newton. All right, so now let's get the direction. We can get the direction by looking at this cross product. So a couple different ways. Here's the way I'm going to do it. I'm going to find the direction of V cross B. So using my right hand, I stick my fingers in the direction of the velocity, curl them into the direction of the magnetic field. My thumb points in the direction of V cross B. V cross B is into the board. However, the charge is negative. So the directional aspect of the force, the directional information contained in this cross product will be the negative of N. So the direction then of the force, of the magnetic force on this moving charge will be out of the board. So my force vector could be written as 1 Newton out of the board. Now, if I wanted to rewrite that in terms of coordinates, I could choose some coordinate axes. Let me choose my x direction to be to the right. Let me choose my y direction to be up. And then to have a right-handed coordinate system, the z direction will be out. So I could also write this using this information and just retranslating it, that the magnetic force is 1 Newton in the z hat direction. Great. So these two expressions contain the same information. All right, so now I want to work this out using full-blown vectors. That is, putting in for the velocity and magnetic field vectors in terms of the x hat, y hat, and z hat unit vectors. So here we go. I'm going to first start by rewriting this. All right, now I'm just going to work symbolically for a while, but putting these vectors explicitly in terms of x hat, y hat, and z hat unit vectors corresponding to the coordinate system that we've chosen on this diagram. So here we go. Now I need the velocity vector. Well, this velocity vector could be written in terms of a vector this way and a vector this way. So the vector in the x direction would be, or the vector component in the x direction would be the magnitude times the cosine of 30 degrees times x hat, to put it in vector form. The one in this component, the y component, would be the magnitude times the sine of 30 degrees. And then to vectorize that, I need to multiply that by y hat. So I'm going to replace this accordingly. All right, now I've got the rest of the cross product. So I've got my cross product symbol. Make sure you keep in mind that's not an X, that's a cross product symbol. And then I've got my magnetic field vector. Well, my magnetic field vector will be the magnitude of the magnetic field multiplied by x hat. All right, so let's just take stock of what we have. We're going to simplify this a little bit before we plug the numbers in. So looking at this, we've got q, v, cosine 30 degrees x hat, cross b x hat. I can pull the b out. So I'd have q, v, b, cosine 30 degrees x hat, cross x hat, and q, v, b, sine 30 degrees y hat, cross x hat. So I have these two products, cross products, x hat cross x hat and y hat cross x hat. Now x hat cross x hat is 0 because any vector, when you take the cross product of any vector with itself, you get 0. That's because the same vector crossed with itself, there's no angle, 0 degrees between those two vectors, and so sine of 0 degrees gives us 0, basically kills off the cross product. The magnitude part does. Now, x hat cross y hat is z hat. That defines a right-handed coordinate system. X hat cross y hat gives you z hat. But if you swap the cross product around and have y hat cross x hat, that gives you minus z hat. X hat cross y hat gives you z hat. Y hat cross x hat gives you minus z hat. So anytime you flip the order of things in a cross product, you introduce a minus sign. All right, so let's work this out. First, I'll work out the first part. Q, V, cosine 30 degrees times B, x hat cross x hat goes away. And then I've got the rest of it. Q, V, B, sine 30, y hat cross x hat, and I'll write that here. All right, the sine of 30 degrees is 1/2. We can now plug in for everything that we have. We'll do that here. All right, so we can finish working this out. The force vector will be, well, let's work out the sign. So I got a minus sign here, and everything else is positive except this other multiplicative minus sign here. Minus times minus gives me plus. All right, I've got 10 to the minus 6 and 10 to the 6th. That gives me 1. I've got 2 times 1/2. That also gives me 1. I've got the z hat direction, and then let's look at the units. A coulomb, meters per second, Tesla, that's a Newton. So basically I've got 1 Newton times z hat. And that agrees with the result we got working this way through cranking through the magnitude and direction separately. So both ways are correct. They have to be correct. One way of looking at a cross product is to construct the magnitude separately and then work out the direction using the right-hand rule. The other way of looking at it is to put all the vector stuff in terms of appropriate unit vectors that you put on your coordinate system and grinding through the vector algebra. The results have to come out the same. This information here contains the magnitude and direction information and vice versa. So both of those mathematical ways of looking at it ultimately are equivalent. They must ultimately give the same result. All right, so hopefully this clarifies to some extent how you calculate the magnetic force that a magnetic field exerts on a moving charge. We looked at it doing two different ways, working separately with magnitude and direction, or working through with full-blown unit vectors on our vector algebra. You should be able to do it both ways. If you can do it both ways, you'll understand this force expression more deeply, and you'll have a better handle on all our vector operations. Thank you.